These are examples for section 13.2, area of other quadrilaterals. Example 1. What is the approximate area of the state of Nevada? Here we have the state of Nevada. It's basically in the shape of a parallelogram. The east and western borders would be the parallel sides for the trapezoid. And then remember, all heights and bases must be perpendicular, so here's our height right here. Height is 309 of the trapezoid and two bases here and here. So for the area of a trapezoid, and of course this isn't exact because the state of Nevada, there's parts of it that don't fit inside the trapezoid, but it's more or less that shape. So we're going to say it's approximately equal to the area. The formula is 1/2 times the height of the trapezoid times the sum of the two bases, B1 and B2. Once we get the formula down, we come over here and we define each variable. Height, base 1 and base 2. For the height is between the two bases, perpendicular. That's 309 or 309 miles. Doesn't matter whether B1 is 205 or 511 because we're adding them. So 205, I'll let B1 be, and 511 miles for B2. At this point, we substitute in values. The area of this trapezoid, representing Nevada, would be 1/2 times the height, which is 309, times the sum of the two bases, 205 plus 511. So there's the formula plugged in with all the values. So then at this point, notice that 309 is an odd number. 2 won't go into it, so I'll keep the 1/2 for a moment. Times 309. Then I've got to add these anyway because they're in parentheses. When I add those two up, we get 716. Now we've got three numbers multiplied together. 716 is even, so 2 will go into it. 2 goes into 2 once, and 2 goes into 716 358 times. So now we have the area is approximately 309, this fraction went away, times 358. Multiplying those two together, our approximate area for the state of Nevada is about 110,622 square miles. Example 2. What is the exact area of trapezoid Pqrs? Here we have a trapezoid. They want us to find the exact area. Locate, the formula is A equal 1/2 times the height times B1 plus B2. We have the height. We've got B1 and B2. We need to define. Well, we've got the two bases, SR and PQ, two parallel sides, opposite each other. But RQ we don't have the length for directly, so we're going to have to find it. So let's go ahead and get the bases down first. I'm going to let B1 be 5, this top base, and B2 be PQ, which is 7. Now to find the height, notice that if we take a straight edge and draw from S, vertex S down, straight down to the opposite side, we've got a right triangle. And of course RQ is the same length as this length right here because they're opposite sides. Well, if we take this triangle and pull it out, notice that it's got a 60-degree angle, so this has to be a 30, 60, 90. So here's our 30-degree angle here. And by the 30, 60, 90 triangle theorem, we've got a ratio of sides. Remember that the ratio of sides for 30, 60, 90 is 1 to the square root of 3 to 2, where 1 represents the short leg, square root of 3 represents the long leg, and 2 represents the hypotenuse. We need the height, which happens to be the long leg right here. So I'm going to place h under the number that is representing the long leg, which that's the square root of 3. So there's the h. I don't need the hypotenuse here, but I do need the short side because, well, actually I don't need that either. Well, I need it to be able to do this. So notice that SR is 5, PQ is 7. So using segment addition, if we take PQ and subtract off SR, we'll get what we need, our short leg. So this right here would be 7 minus 5, which is the same as from here to here, which of course gives us 2. So 2 goes underneath the short leg. So we're not using the hypotenuse number, and now we have this ratio of 1 to 2, and the other ratio is square root of 3 to h. So we set up a proportion out of it and cross multiply. 1 times h is h, and 2 times the square root of 3 is 2 times the square root of 3. So now that we have h, it's exactly 2 times the square root of 3, and that would be meters. All of these are in meters. Once we've done that, we've defined all our variables. We come back over to our formula and we substitute in what we have. We have 1/2 times the height, which is 2 times the square root of 3, times the sum of the two bases lengths, 5 and 7. So there's the plugged in step there. Notice that in 1/2 times 2 times the square root of 3, these two factors, 2 is a common factor. So 2 goes into 2 once, 2 goes into 2 once, and we're left with 1 times the square root of 3, which gives us 1 times the square root of 3, or simply the square root of 3, times, and then we need to add these two inside the parentheses. 7 plus 5 is 12, and we get the area, the exact area of this trapezoid is 12 times the square root of 3 square meters. Example 3. What is the area of kite KLMN? So here we have a kite, and of course in a kite, pairs of consecutive sides are congruent, so KL is congruent to KN, and LM is congruent to NM. And in the kite, we have diagonals KM and LN. We're trying to find the area, and the area of a kite is 1/2 times the length of one diagonal times the length of the other diagonal, D1 and D2. So we need to find or figure out what D1 is and D2. So I'm going to let D1 be KM, this first diagonal. It's a little longer. We use segment addition. Take this portion of it, which is 2, and we add to that this portion of it, which is 5, and we get 7 meters for diagonal 1. For diagonal 2, we're going to use the other diagonal, LN, which is 3 plus 3, adding the two segments here, which of course gives us 6 meters for diagonal 2. Now we have everything we need to use here. So we come back over here, and the area of this kite is 1/2 times D1, which is 7, times D2, which is 6. Notice that 1/2 and 6 will both reduce down, so we have 2 goes into 2 once, 2 goes into 6 3 times. Now we have 7 times 3, or simply 21 square meters. And this is the area of the kite in square meters. Example 4. The high occupancy vehicle, or HOV lane, is marked by a series of diamonds, or what are really called rhombuses, painted on the pavement in one lane of a freeway. What is the area of the HOV lane diamond shown below? So these diamonds, Lubbock's not big enough to have these kinds of lanes, but you'll see these in Dallas-Fort Worth, Houston, Austin, San Antonio, those places. And so you'll see this rhombus, and they didn't name all 4 vertices here, but they did name 2 of them, plus the intersection of the 2 diagonals. Remember, the diagonals in a rhombus are perpendicular to each other. So here we have this particular side here, 6.5. And then they give us part of one of the diagonals, half of it. Remember, in a parallelogram, in a parallelogram, the diagonals of a parallelogram bisect each other. So if BC is 2.5, then the other end over here has to be also 2.5. In other words, we double BC. So to find the area, it's the same formula as for a kite. It's 1/2 times the first diagonal times the second diagonal, D1, D2. So now let's define D1 and D2. D1 I'm going to let be this shorter diagonal here. So D1 should be the length of BC doubled, or 2 times BC. Well, this will be relatively easy to find. D1 is 2 times BC, which is 2.5 feet, and that gives us 2 times 2.5 gives us 5.0 feet, or 5 feet. So there's our first diagonal. Now our second diagonal, we're going to use AB and double it for this longer one. So it would be 2 times AB, the length of AB. We don't have the length of AB yet, so we need to find it. Take this triangle out. Here it is right here. And AB is the longer leg of a right triangle. We've got 2 of the sides of the right triangle, so we'll apply the Pythagorean theorem. We can use that to find this other side. So take the hypotenuse AC, which is 6.5, and square it. And that's going to equal the length of AB squared plus the length of BC, which is 2.5 squared. Solving this, take your calculator. 6.5 squared will give us 42.25 equals AB squared plus 2.5 squared gives us 6.25. Solving for AB, we need to solve for AB squared first, so subtract 6.25 from both sides. When we do that, AB squared gives us exactly 36.0, or 36. That's convenient because 36 is a perfect square. When we take the square root of both sides to get rid of the square on the AB, to find what AB is, we take the square root of 36 and get 6. So now that we have AB here, we can now double it for the entire diagonal. So D2 is 2 times AB, which we found was 6, which gives us 12 feet for diagonal 2. Now that we have both diagonals, we can now use them in the formula for the area. So finding the area of the surface inside this rhombus, we have 1/2 times D1, which is 5 feet, times D2, which is 12 feet. 1/2 and 12 will both reduce out. So 2 goes into 2 once, 2 goes into 12 6 times. And the area is 5 times 6, or simply 30 square feet. So there's 30 square feet of surface inside this rhombus on the freeway, the asphalt or the cement, whatever it's made of. Example 5. Write a formula for and find the area of the composite figure below. This is a composite figure because it has 2 or more other simpler figures that are added together, non-overlapping parts. And so we've got this shape or figure here. So first of all, we want to write a general formula for the area of the composition of these right here. Notice we've got a kite, and we've got 2 trapezoids. Notice this trapezoid here and this trapezoid here are congruent trapezoids. One of them has just been simply flipped over to the image of the other. So we can write, we've got the area of a trapezoid, but there's 2 of them that are congruent, so 2 times the area of a trapezoid. Then we're going to need to add to that this kite's area, so that plus area of the kite. So there's our general formula of what we're going to use here. At this point, we want to define the variables, all the lengths that we need. So we're going to take, first of all, let's take the trapezoid and then skip a little space and we'll take the kite. In the trapezoid, remember we've got two bases and a height. So there's B1, there's B2, and there's the height. And then in the kite, we use diagonals to find them. We've already got one diagonal drawn here, D1, but then there's another diagonal that we're going to need to draw and figure out. So D1 and D2. Notice none of these variables are the same. So let's go through and figure out which is which. Take one trapezoid, like the one on the left. Notice that the two sides that are parallel to each other are the bases. And so 6 and 4 would be B1 and B2. It doesn't matter which goes where. I'm going to let this top one be B1 and this bottom one here be 4. Then the height has to be perpendicular to both bases. It's perpendicular here, and by definition it's perpendicular up here, and so the height is 3. So that was relatively easy. It's the same over here, of course. Now for the kite, one of the diagonals, the one that's drawn, obviously is 10 yards. So I'm going to get that one down. The other diagonal, take a straight edge, and I'm just going to draw half of it to complete this first trapezoid up here. Take a look at from here to here and from here to here. This right here is the difference between those segment lengths. So this is 6, and if I subtract 4 from it, 6 minus 4, I'll get the length of half the diagonal. That's 2. So the whole diagonal, of course, by definition, these are going to be congruent, so that would be 2 times 2. Or we can write for our notes 2 times the 6 minus 4. And so diagonal 2, or D2, is 2 times 6 minus 4 is 2. 2 times 2 is 4. So our other diagonal is 4 units across, or 4 yards across. Now that we have everything we need, D1 and D2, B1, B2, and H. None of these are being shared, and so we don't have to worry about renaming any of these. Now that we've done this, we come back over and write a more complex formula for the area of the composition. So the area of the composition is 2 times the area of a trapezoid. The area of a trapezoid formula is 1/2 times the height times B1 plus B2 plus the area of the kite is 1/2 times diagonal 1 times diagonal 2. Then we try to simplify as much as we can. Notice that there are two terms. There's this term, this first term here. Everything in here is multiplied together with the parentheses. Everything in the parentheses is multiplied together with everything out here. And here's one term over here. So notice the 2 and 1/2 will both kind of cancel each other out. So 2 goes into 2 once, 2 goes into 2 once. So I'm going to rewrite this as 1H, or simply H, times B1 plus B2 plus 1/2 times D1 times D2. Now, neither one of these terms have a common factor in them. These D1, there's no D1 over here, there's no D2 over here, there's no B's over here or H's, and then 1/2 doesn't have a common factor here anymore either. So this is as simple as it gets. So the area of this figure right here, here's the formula for it right there. And so there's your first answer. Now to actually find the area, we substitute in all the values we found. So the height of the trapezoid is 3 times B1, which is 6, plus B2, which is 4, plus 1/2 times D1, which is 10, times D2, which we found was 4. Now over here on the right, trying to get rid of the 1/2, it doesn't matter whether we use the 10 or the 4, but just don't use both. I'm going to use the 10 simply because it's a factor right next to it. But so 2 goes into 2 once, and 2 goes into 10 5 times. So now we have 5 times 4 times 1, or just 5 times 4. Over here we have 3 times 6 plus 4. We're going to add those first. 6 plus 4 is 10, plus, that's gone, 5 times 4. Now the order of operations tells us that requires us to multiply before we can add. So 3 times 10 is 30, plus 5 times 4 is 20, and we do get 50 square yards for the total area of this composite figure. That's all of this right here. Area of exactly 50 square yards. Example 6. Now we turn our attention to coordinate geometry. Find the exact area of quadrilateral QRST using any coordinate geometry formulas needed. So we want the exact. Notice we have this kite. Actually, this was supposed to be kite. I think I changed it on your notes. And in this kite, notice we have QT and ST are both congruent consecutive sides, and QR and SR are both congruent consecutive sides. Well, to find the area, of course, we're going to need diagonals. So it's 1/2 times diagonal 1 times diagonal 2. We need to draw the diagonal, so take your straight edge and draw diagonal RT. And then draw diagonal QS. Remember, the diagonals in any kite are perpendicular to each other. We may or may not need that fact. One thing we do need, and since we need the lengths of these, we're going to have to use the distance formula because neither one of these segments or diagonals are vertical or horizontal. So we need the ordered pairs for all the endpoints or vertices. I'm going to start with Q. Q is at 0, 3. And then we have R is at 5, 5. And then we have S, which is at 3, 0. And finally we have T, which is at a very convenient place, 0, 0. So our diagonals are QS and RT. So I'm going to start with diagonal 1. I'm going to start with RT. That's RT. And that's equal to the distance formula. Well, if we're going to use RT, we use these two right here. And we're going to use the formula. I'm going to let T be my first point, and this be my second point. So I'm going to start with 5. We have 5 minus 0, quantity squared, plus, and then back over to the y here, 5 minus 0, quantity squared. So diagonal 1 gives us 5 minus 0 is 5 squared, plus 5 minus 0 is 5 squared. So D1 is the square root of 5 squared is 25 plus 5 squared is 25. This gives us the square root of 50. Now we simplify that. We don't approximate because we need exact. So let's go ahead and simplify the square root of 50. The perfect square factor of 50 would be 25. 25 times 2. So we have 25 times 2. And then the square root of 25 is 5, so it comes out. So D1 is 5 times the square root of 2. The 2 is still underneath. So there's D1. Now for D2, you find D2, and before you go on to the area formula, go ahead and stop. Okay, for D2, that would be QS, which we're using the distance formula. We're going to use these two right here. Okay, this time I'm going to start with the x coordinates, of course. I'm going to start with 3, this one right here. So that would be 3 minus 0 squared plus, back over to the y coordinate here, that would be 0 minus 3 quantity squared. So D2 is equal to 3 minus 0 is 3 squared plus 0 minus 3 is negative 3 squared. Don't forget your parentheses. So D2 is the square root of 3 squared, which is 9, plus negative 3 squared, which is also positive 9. And so D2 gives us the square root of 18. We need to simplify the square root of 18. The square root of 18 factors into 9 times 2. 9 is a perfect square, so we have 9 times 2. The square root of 9 is 3. So that we pull out the 3. There's still a 2 left under the square root. So D2 was 3 root 2. Now that we have both diagonals, we can now use them in the formula for the area. The area is equal to 1/2 times d1, which is 5 times the square root of 2, times d2, which is 3 times the square root of 2. Now 2 will not cancel out either with 5 or 3, and we can't cancel it out with 2 because 2 is underneath the square root. So we're kind of stuck with the 1/2 right now. So area is 1/2 times 5 times 3 is 15. The square root of 2 times the square root of 2 is the square root of 4, which is simply 2. So we've multiplied these two together to give us this. Now 1/2 does have a factor it can cancel that with, 2 and 1/2. So 2 goes into 2 once, 2 goes into 2 once, and we're left with 1 times 15, or simply just 15, and this is exact, happens to be a whole number, 15 square units. So there's exactly 15 square units in this kite here. Example 7. A kite has an area of 5 square inches. So the area of this kite is 5 square inches. Find the lengths of each diagonal, D1 and D2, if one diagonal's length is 7 less than 6 times the other. So we don't know either diagonal right now. Let's go ahead and label this. This long one here I'm going to call, I guess, D2. And this shorter one here I'm going to call D1. Let's go ahead and set up what both our diagonals need to be. Well, we know we're going to find the area, so let's go ahead and get that down first. The area is 1/2 times the first diagonal times the second diagonal. Now we need to define these diagonals. Let's let x, or any variable you want to use, I'm going to use x, equal the first diagonal, or one of the diagonals. It says if one diagonal's length is 7 less than 6 times the other. So really, I just let x be the other diagonal. It's the independent variable. The other variable, for the other diagonal, is going to depend on what this one is. So this one's x. Then it says, back to what we were just reading, if one diagonal's length, that's this new one now, D2, is 7 less than, so we're going to subtract 7 from something, 7 less than 6 times the other. Well, the other is x, and we're multiplying it with 6. So 6 times the other minus 7 is one diagonal's length is 7 less than 6 times the other. So this is the other diagonal. So we have x for one diagonal and 6x minus 7 for the other diagonal. Now we already know the area is 5, so I'm going to plug in 5 where the a is, equals 1/2 times, then we have the first diagonal x times the second diagonal is 6x minus 7. So now we have this equation. We need to find x. Now they're asking us to find the length of the diagonals. So after we find the x, we've already found one diagonal because it is x, and then the other one we're going to need to substitute in here to find the length of it. So our objective now is to solve this equation. First of all, I'm going to kind of clean things up, simplify a little bit. I noticed that I'm going to leave the 1/2 out. I'm going to use the x, and I'm going to distribute it with everything inside this binomial here. So I have 5 equals 1/2 times, and then x times 6x is 6x squared minus 7x. Now I'm going to get rid of the 1/2 by multiplying both sides of the equation by 2 so I can get rid of that fraction. When I do that, the left side changes now to 2 times 5 is 10. On the right side, the 1/2, which is a factor of all of this, cancels out with the 2. They can both go one time, and we're left with just this part right here, 6x squared minus 7x. Notice we've got an x squared and an x term, so we need to get everything set equal to 0. We have a quadratic. So I subtract 10 from both sides, and I get 0 equals 6x squared minus 7x minus 10. So here's our quadratic, and it's an ax squared plus bx plus c form. Now, if we try to factor it, we could use the quadratic formula. Since a is something other than 1, our factoring is going to be a little bit more difficult. So I'm going to use the quadratic formula here and see what we get. Remember, the quadratic formula is x equal negative b plus or minus the square root of b squared minus 4 times a times c under the square root, all divided by 2a. Let's identify what a, b, and c are here. A is 6. B is negative 7. And c is negative 10. So now we use the formula. Everywhere we see a, b, and c, we go ahead and substitute in those values. Let's keep track of what we're doing and try not to run out of room. Give yourself plenty of room. So here we go. Starting with x here. X equals negative b, which is negative 7. So we have negative 7, plus or minus the square root of b, which is negative 7, squared, put it in parentheses, minus 4 times a, remember this is all under the square root, a, which is 6, times c, which is negative 10. Be careful with your negative signs. All divided by 2 times a. 2 times a, which was 6. So here is your plug-in step right here. Now this is going to get relatively easier to look at here in just one step. Negative 7, or negative 1 times negative 7 is positive 7, plus or minus the square root of negative 7 squared is 49. Now we subtract, or you can look at this as plus negative. Negative times positive times negative. You have two negatives, so that's going to end up giving you a positive value. So we take these numbers and multiply them together. 4 times 6 is 24. 24 times 10 is 240, but it's positive because there's two negatives. So plus 240 underneath the square root, all over 2 times 6, which is 12. See, it's already a lot simpler. So then continuing, we have x equals 7 plus or minus, we need to add these two under the square root. 49 plus 240 gives us 289 over 12. Then 289 is a perfect square. That means this possibly could have factored. 7 plus or minus 17. The square root of 289 is 17 over 12. Now when you get to this point and you still have the plus or minus, you separate it into two. You have 7 plus 17 over 12 and you have 7 minus 17 over 12. So let's write those down. X equals 7 plus 17 over 12, or 7 minus 17 over 12. So we have our two solutions for x possible so far. 7 plus 17 gives us 24, so we have 24 over 12. Or x could be 7 minus 17, which is negative 10 over 12. Over on this first one, 24 divided by 12, or 24 twelfths, reduces to 2 ones, or just 2. And over here, when we reduce negative 10 twelfths, we get negative 5 sixths. It reduces by 2. So x can either be, right now it can either be 2 or negative 5 sixths. Now if we use negative 5 sixths, a diagonal's length has to be positive. So already we know that this one won't work because it's negative. So the 2 is what we're going to use. So therefore, diagonal 1 is equal to x, which is 2. There's our first diagonal. This one's 2 units long. The other diagonal, diagonal 2, is 6x minus 7. So that would be 6 times x, which is 2, minus 7. So d2 is 12 minus 7, which is 5. So we found both diagonals of this kite. We were just given the area and some information about the diagonals. D1 is 2 units long, or actually that'd be inches, and D2 would be 5 inches long. And those are your two answers.